It's a great pleasure to be here at Michigan, and particularly it's a great honor to be able to give the Taiyu Wu lecture. I've had the pleasure of spending a month at AJIA in Taiwan. I actually had a wonderful month where my daughter, who was studying Chinese in high school, had gotten into college. I took a month off, spent a month at AJIA. She came with me, the two of us shared an apartment in Taipei for a month. It was a really wonderful time to be kind of with your 17-year-old before she goes off to college. So I have a very fond memory of Taipei and, fond memory of, what Professor Wu accomplished in really building Taiwanese astronomy. So today what I want to talk about is, in many ways, the tremendous progress that we've made in the field since Katie and I were working together in Boston in the mid-'80s. And it has been a remarkable time. When we entered the field, we had a really wide range of possibilities about what the properties of the universe were, what made the galaxies we see, how did structure emerge. And what we have found is that the universe has turned out to be, as from what we've seen so far, much simpler than we thought it would be, remarkably simple, as I'll stress in my talk, in its properties, but also very strange. What do I mean by that? When I say the universe is simple, I'm saying with a handful of numbers, the age of the universe, the density of atoms, the density of matter, how lumpy the universe started out, and how that lumpiness varies with scale. So effectively, with 5 numbers, I can fit millions of independent observations. We'll show you pictures of the microwave sky, the leftover heat from the Big Bang, and you'll see that we've made millions of independent measurements, measurements of large-scale distributions of galaxies, measurements of the expansion rate of the universe, chemical properties of the universe. All the basic things we see can be fit by just these basic numbers. It's one of these simple models that, to me, is the most remarkable thing about our universe. I mean, to me, this goes back to, I was just talking to my son, who's taking high school chemistry, that you look at that periodic table and all the complex stuff that makes up the periodic table, or that makes up our atoms and coats and molecules are all made from a handful of atoms, and then we realize those atoms are just made from protons and neutrons and electrons. And this is, I think, the great shock of modern physics. The universe is fundamentally simple, and at a basic level, there's a handful of numbers, a simple theory we need to characterize things. And we've learned that in laboratory physics over the past several centuries, I guess. And now we're learning this again in cosmology, that with these 5 numbers, we fit all the properties of the universe. But while the universe is simple, it's strange and filled, I think, for us now with a deep mystery. Atoms, the stuff that make up us, makes up only 5% of the universe. So I feel we have this moment of being the glass half full, that with great confidence I tell you we have a model that fits all this data, and that'll be the theme of much of my talk. But also with great, I would say, both embarrassment and excitement that we don't know what 95% of the stuff is there. We don't know what the dark matter is. We don't know what the dark energy is. We don't really understand the origin of what drove the fluctuations. We have this idea called inflation, which I'll say a little bit about, but there's a lot of missing pieces and a lot we need to learn, and that makes things exciting because discovery awaits us. In order to give you a feel for cosmology, we have to begin by introducing some basic concepts. I'm going to spend the first minute teaching you special relativity. The key idea for us today is that light travels at a finite speed. It takes a few billionths of a second for light to get from me to you. You don't see me as I am at this moment. You see me as I was a few billionths of a second ago. doesn't matter much. I don't change that much in a billionth of a second. The further out you look in space, the more significant that becomes. We see the sun as it was 8 minutes ago. For those of you who've seen that, the wonderful movie The Martian, they very nicely convey takes 30 minutes sometimes for the signal to get back and forth to Mars. And you say hello, and it takes an hour to get the answer back. And the further out you go in space, the further back you go in time. When we see a star in the night sky that's 10 light years away, we see the star as it was 10 years ago. And if you were on a planet orbiting around that star, observing us, you would see us as we were 10 years ago. So the further out we go in space, the further back we look in time. A nearby galaxy we see as it was 1 million years ago, a more distant galaxy 100 million years ago, and some of the most distant galaxies we see with the Hubble telescope, we see them as they were, say, 12 billion years ago. Much of what I'll talk about is observations of the microwave background, looking out and seeing the universe as it was 13.7 to 13.8 billion years ago. So the first idea, the further out you look in space, the further back you look in time. Everyone's got special relativity down? Excellent. Next, general relativity. The key idea in general relativity, as my academic great-grandfather taught, Johnny Wheeler, matter tells space how to curve. The curvature of space tells matter and light how to move. So that means that light traveling from a star towards us, passing by the sun, a star at position A, its light gets bent as it propagates around the star. And when we observe it on Earth, we don't see it at position A, but at position B. This is the famous bending of light that was predicted by Einstein. And here is the 1919 New York Times announcing that the light is all askew in the heavens. This was 1919, so it's men of science, more or less agog over results of eclipse observations. This is, of course, incorrect. The stars were indeed not where they seemed, but the important thing is where they were where Einstein calculated them to be. And this is the first great confirmation of the theory of relativity, general relativity. We'll get back at the very end of the talk to this very recent, very impressive confirmation by Ligo. That's what we're going to end with. And this gave us this theory of general relativity that becomes the language we use for talking about space and time. An interesting history of science note on this is when Einstein first developed his theory of general relativity, his first version was not the final version. It was not correct. It was off by factor 2. And he had published a prediction in 1915 of light bending that they had tried to test with an eclipse expedition. Einstein was lucky, it was cloudy, they weren't able to make the measurement. Subsequent to that, he did the right calculation, got the right prediction out, and then the observation was made. And it would have been interesting, I think our view of general relativity would have been different had the measurement been made, then he made the correction. So it's sometimes, for astronomy, clouds are good. Now, once you start with general relativity, we're now going to confront what I think for most people is really the most conceptually difficult idea, and that's the idea of the expanding universe. So the general relativity says that we shouldn't think about things in terms of absolute distance, that space is this absolute thing that we should think about, but only in terms of relative distance. And what I do is I tell you, how long it takes to travel from New York to London, London to Tokyo, and Tokyo to New York. That information alone, the fact that you can make a trip like that, tells you that the Earth is a sphere and it's not flat. So in relativity, we specify distances, and that tells us the structure of space. What general relativity tells us is that if I start with a uniform universe, it will either expand or contract, and what we observe, it's expanding. What do we mean by that? Is that the distances between galaxies are constantly growing. The picture to have is that the universe started out very dense, and over time, it expanded and got bigger and bigger. This is a two-dimensional picture of the universe. We imagine ourselves living on the surface of a sphere, and the radial direction is time. So you should think about the universe expanding into the future, and as we go deeper into the future, the universe gets bigger and bigger. So the radial direction in this ball is time. Here we are today. Here is the future. In the past, the universe was denser. Galaxies were closer together. In the past, the universe was also hotter. So as we go back in time, the universe gets denser and denser, hotter and hotter, until we go back to the moment of the Big Bang, the initial singularity, which in the standard picture becomes infinitely dense, infinitely hot. You'll notice the Big Bang doesn't happen in a particular place. This happens everywhere. If you take a ball and deflate it to a point, every place on the surface returns to that point. So given that picture, we can now construct a quick history of the universe. The universe starts out very, very dense, very, very hot. As it expands, it cools. During the first few minutes of the universe's history, most of the light elements in the universe, most of the helium and deuterium form in those first moments. About 500,000 years after the Big Bang, the universe gets cool enough, remember, as it expands, it gets colder, that atoms are able to form. Once atoms form, the universe becomes transparent to the microwave background. This background radiation is a leftover heat from the Big Bang. And when we look at the pictures I'll show you soon of the microwave background, we're looking at light that's propagating from when the first atoms formed 500,000 years after the Big Bang to today. And that's what the pictures are. They're pictures of what the universe looked like back then when we look out at the sky. Give you a sense of progress in the universe. About 100 million years after the Big Bang, stars start to form. About 1 billion years, galaxies and quasars of the size we see emerge. Our own solar system formed about 9 billion years after the Big Bang, and our solar system and our sun's about 4.5 billion years old. So the age of the solar system is roughly a third of the age of the universe. Life seems to have emerged pretty quickly once it cools down. So I've talked a bit about the cosmic background radiation. This is the leftover heat from the Big Bang. Whatever direction you look, you see this radiation. Those of you old enough to not have cable TV and to have watched TV with an antenna and switch between stations, when you switch between stations, you saw static. About 2% of that static was due to the cosmic background radiation. Most of it was from the ground, but about 2%, so it's non-trivial, was just you were observing the leftover heat from the Big Bang. So in a sense, it's pretty easy to observe, and it's everywhere on the sky. What was the great challenge was to see the fluctuations in the background, and these were first seen by the Planck Satellite, and these fluctuations were very small. So while the microwave background was at a temperature of about 3 degrees above absolute zero, the fluctuations that were seen by Planck were of about 18 microkelvin, or millionths of a degree. So they're 10 to the 5 times smaller. So it's basically the difference between seeing the Earth's surface and seeing tiny hills on the Earth. So that, from a distance, the Earth looks like a sphere. You've got to look really carefully to see the hills and valleys. And these microwave background fluctuations we see here are the hills and valleys. Now, when you look at this COBE picture, so COBE was launched in 1989 by NASA, saw the fluctuations. The COBE discovery won the Nobel Prize in 2006. You see this big red band across the center. That's not emission for the microwave background. That's our own galaxy, the Milky Way. The galaxy is filled with dust, with electrons. Those also emit at radio frequencies. And one of the challenges we have in astronomy is when you look out, you also look through the galaxy. And one of the things we'll do, and this will be a theme we'll touch on a couple times, is we have to separate the galaxy from the observations. So next we'll turn to, and Katie mentioned, the Wilkinson microwave anisotropy probe. Was Wilkinson a PhD here? Yes. So Dave Wilkinson was a Michigan PhD and was one of the pioneers of microwave background research, played a key role in getting this experiment started, sadly passed away from cancer soon after we got our first data. NASA generously let us rename the experiment after him, the Wilkinson microwave anisotropy probe. And this experiment was launched by NASA out to what's called the second Lagrange point, a point about 4 times the distance of the moon, where you can orbit with the Earth and Sun at your back and a satellite looking out, mapping the heat from the microwave background. And what we're doing is looking out to this moment where the universe made the transition from being ionized to neutral. So here's some of our images of what we saw in the microwave background. These are pictures of the galaxy, first in bright red, and these are fluctuations you see. We observed at many different frequencies, 5 frequencies with WMAP, and as you go up in frequency, you see the galaxy get dimmer. So you can use this multi-frequency information to separate out the galaxy. And you notice if you'll focus on a given region that the pattern stays the same as you go up in frequency. And that's one way we know that these fluctuations are thermal. We can combine them and make an overall clean map of the microwave background. And this sort of represents our baby picture. This is what the universe looked like 500,000 years after the Big Bang. And what you're seeing here are tiny variations in density from place to place. And these are these tiny variations in the universe's temperature. And it's these tiny fluctuations that will grow to form galaxies. I should draw your attention to the letters SH that appear pretty clearly here. This represents probably not an important signal from the early universe. It's not telling us that Stephen Hawking is playing a unique role. I think it's actually telling us that our brains are really good at finding patterns. I like to think of this as evolution selects for those of us who think we see tigers in the grass. So imagine there are 2 sets of humans. These are calm humans. They say, it's probably not a tiger. These humans are jumpy humans. Every time they see something, they jump. They're very jittery. They're kind of nervous, a little annoying. But 1 time in 10, they're right. And these guys get eaten, and the ones over here to survive to be our ancestors. So we're kind of all like these guys here. And we're good at finding patterns when they're not there, which is why we need to do statistics to test ideas and test the validity of things. And one of the statistics we'll do, and I'll show you this, is we basically throw down circles like this, and we measure how lumpy the universe is. What's the amplitude of temperature fluctuations smoothed on this scale? And I'll show you a few plots, and those are measurements of what is the amplitude of fluctuations versus scale, and that's what we're showing here. So this is as a function of, for the experts, multipole moment, for everyone else, 180 degrees divided by the angle. So this is what the fluctuations are at 1 degree, at 10 degrees, and 1/10 of a degree. And the points here are the data. This is from our WMAP data. And the curve is the model. And the first takeaway is we're able to make these really accurate measurements, and the model matches the data. And this, as you can see, there's a lot of structure in the data. We can read off from this that the typical amplitude of fluctuations is about 1 degree. That's nature holding up a ruler for us. We know how far sound waves can move in the age at that point. So we know how big the fluctuations are. Nature holds up a ruler. We can measure straight from that the geometry of the universe. And it's actually nothing more than high school geometry. You've got one length here, you've got an angle, you measure the sides of the triangle. And from that you get the age of the universe. The age of the universe is how long it propagates. So that's really simple technique. This gives us an age of 13.7, 13.8 billion years. And similarly, we could read off things like the relative amplitude of the first to second peak tells us how many atoms there are in the universe. So relatively simple analysis fits this data. Once you've measured those initial fluctuations, seen what the universe looks like a few 100,000 years after the Big Bang, you could take your computer simulation, and people like Gus Everard here run these simulations where you run this forward in time and gives you a distribution of galaxies which you can compare to the observed distribution. And when you do that, you can take this model, fit to the data 500,000 years after the Big Bang, and compare it to all these things we see. Distances to supernovae, measurements of the expansion rate of the universe, the Hubble constant, estimates of the age of the universe based on the age of oldest stars, properties of clusters of galaxies, abundances of elements like helium and deuterium. All the pieces fit together. We have a simple model that fits. And here's a plot I like from René Lozek that shows what is the amplitude of fluctuations in mass, how lumpy things are, versus mass scale, going from 1 billion times the mass of the sun, size of a galaxy, up to the mass of the visible universe, roughly 10 to the 23 solar masses. The points are the data, now showing data from WMAP, from the ACT experiment on smaller scales, and in the nearby universe from things like the Sloan survey and measurements of clusters. And the curve is our model of what our simple model predicts. The points are the data, and the model fits over a range of more than 1 trillion in mass and more than 100 million in time. So data fits a few 100,000 years after the Big Bang when we look at the microwave background. It fits the abundance of helium a few minutes after the Big Bang, and it fits the observed properties of the universe today. So that's a pretty successful model, even though we had to invent dark matter and dark energy. All right, so we've got a good model. It fits the data. What do you do next? Well, it's a strange model. You'd like to really test it. You'd like to get better data. One of the next steps in doing that is we go out and we launch the next satellite. And the European Space Agency launched the Planck Satellite about a decade after WMAP. And over the last couple of years, it's reported its results. First thing that Planck has shown us is it's gotten a very consistent picture of what you see. Smooth to the same scale. One plots the WMAP data, the other plots the Planck data of what the microwave sky looks like. Pretty good agreement. And we can now get more quantitative. It's just comparing pictures. We can compare the fluctuations versus scale. This is over the scale where the WMAP data is valid. The black points come from cross-correlating WMAP and Planck. The red points come from Planck alone. And the data agrees really well. You'll notice that the WMAP data is noisier. The Planck data is higher precision. It's a follow-up satellite. But the overall agreement's excellent. And we can also compare what we see from Planck with the measurements we make from the ground. And these show observations of a small patch of the sky at 2 different frequencies from Planck, and above 2 different frequencies for measurements that our experiment in Chile, the Atacama Cosmology Telescopes made. Jeff McMahon here is a key part of the ACT team, and we've made these detailed maps of the sky. And it's, to me, really remarkable that you could launch these experiments to deep space, very complicated experiments. You build experiments on the ground where you have to observe these tiny fluctuations. Remember, these fluctuations are a few millionths of a degree. We're observing them through the Earth's atmosphere, and we see the same thing. It's tremendous, even before we get to the triumph of the theory in fitting the data. It's a tremendous triumph for my experimental colleagues that all these independent experiments, measuring things with different kinds of detectors, using different techniques, all fit together. And this shows flashing back and forth between what we saw from 9 years of WMAP data, data from the Atacama Cosmology Telescope, data from the South Pole Telescope at the South Pole, and the Planck data. And you can see that over this very large range of scale, so a factor of 1,500 in scale, remember this measures 1 over a degree. This is how lumpy the universe is versus scale, what the temperature fluctuations are, that the data agrees between the different experiments. That's the first big step. And the model, which is the black line, goes through all the data. So we have a very consistent picture. Not only can we look at the temperature fluctuations, we can look at fluctuations in the pattern of polarization. And again, this is model versus data. The polarization patterns, model versus data. And up top, we're looking at the distribution of galaxies. The same physics that leads to these fluctuations in the microwave background, basically sound waves moving near the universe. The physics basically comes down to you take a region, you make it denser, it generates a sound wave that propagates out. And that sound wave gets frozen in into the pattern we see in the sky when electrons and protons combine to make hydrogen. And that pattern is associated with an excess of atoms in a ring around it. So you've got that excess density. That excess density shows up in the distribution of galaxies. This top plot comes from the Sloan Digital Sky Survey, which has mapped the positions of millions of galaxies. This is the correlation in galaxy positions, actually measured. And the points are the data. The curve is a model where you fit to the theory of the microwave background. You fit to the universe 500,000 years after the Big Bang. You predict how galaxies should be distributed in the nearby universe. You measure the position of 1 million galaxies. And the data and the theory fit. So we really have a consistent story of how structure emerges. This is looking at the same picture. Now, instead of looking at those power spectrum, we're going to each cold spot in the map. So we go back to these pictures, go to every cold spot on the map, stack everything around that cold spot, and this is the pattern. Let's see if I get this right. On top is what the data shows. On the bottom is what theory predicts. This is the same thing stacked around each hot spot. Around each hot spot, you see there's a cold ring. Every hot spot in the sky has a cold ring around it that's about 1 degree across. That corresponds to how far that sound wave could move. You had excess matter that sent out a sound wave, and that produces that ring here, similar ring here. And the size of that ring is telling us the age of the universe. That's that ruler we hold up here. And the exact shape of the ring gives us things like the density of atoms and the density of matter. Here's our Sloan survey and these sound waves in the sky. So after the WMAP data, we had a consistent cosmology. After the Planck measurements, and we now have complemented by things like measurements of gravitational lensing of the microwave background, the precision of our data has improved over the past decade, and the model still is remarkably successful. But as I stressed in the introduction, while the model is successful, it has many big open questions. And to me, among those big questions are understanding what's the dark matter that makes up most of the massive galaxies? What's the dark energy that dominates the energy density of space and drives the universe's acceleration. And why are there atoms, so-called baryogenesis? Why is there more atoms and matter than antimatter? And finally, what generates the fluctuations we see? Why is the universe not uniform? What's the origin of the universe? Our best idea at the moment, not their only idea, but in many ways, or at least our most popular idea, about what generates those fluctuations is the idea of inflation. It's the idea that if we look at the size of the universe versus time, instead of expanding at a sort of relatively constant rate, that the universe in its earliest moments, 10 to the minus 35 seconds after the Big Bang, so really early on, underwent an incredibly rapid period of expansion called inflation, where it grew in size by more than a factor of 10 to the 40. So in this brief moment, it expanded truly exponentially. And this idea, when it was presented and developed in the early 80s, to me seemed incredibly remarkable, in that it suggested first that the universe could accelerate, then it suggested that the universe should be flat and uniform, and made all these very particular predictions about the universe's properties. It predicted that the geometry of the universe should be flat, that there should be fluctuations on scales larger than the visible universe given its standard model, which is superhorizon. It predicted the fluctuations are what we call adiabatic, which means when we have more photons, we have more electrons, we have more dark matter. The composition of the universe is the same over there as it is over there. What varies is the density from place to place. It predicted that the fluctuations are what we call Gaussian, equal number of hot spots and cold spots, that the fluctuations are drawn from a distribution that looks like this, where we look at the number of fluctuations versus temperature. And this curve, which seems not to reproduce very well on the screen, is the prediction of theory. And you can take those maps and count how many spots do you have at 0, at the average temperature, at twice the average temperature, at -2, and that's the data. And you plot up the hundreds of thousands of independent points on the sky, and they have just the Gaussian curve you predict. So the statistical properties of the fluctuations all look remarkably simple. Not only that, one of the strangest predictions of this model is that the universe can undergo a phase of acceleration. At the time it was suggested in the 80s, this was something that seemed very surprising. Yet today we see the universe is accelerating now. So the idea that it could have accelerated in the past does not seem so bizarre. So inflation, as a result of these successes, has emerged as a very popular explanation of what happened in the first moments of the universe and what led to the fluctuations we see in the microwave sky. Now, this inflationary model is not without its critics, and it is certainly an incomplete model in that it doesn't explain how the universe began, what was there before inflation. We have not connected the ideas of inflation fully with our ideas in particle physics. There's lots of work on that, but still much to be done. What most of us see as the next step in testing this inflationary idea is the idea that the model predicts not only should there be variations of density produced during that period of acceleration that we see as the galaxies we see around us in the microwave background fluctuations, but there should be gravitational waves generated in the early universe. And these gravitational waves have sort of become the holy grail of cosmology. And the way we want to look at them is look at them by looking at patterns of polarized light. What do we mean by that? Well, to explain that, I have to remind you that light is an electromagnetic wave. And as it propagates to you, it can propagate with the electric field pointing this way, or the electric field pointing that way, or that way. Those are all different polarizations of light, all depending on the orientation of the electric field. unpolarized light has equal numbers of photons in each polarization. The light coming from the incandescent bulb or the sun is typically pretty unpolarized. On the other hand, if you have light scattering off of a surface, it tends to scatter more in this polarization than that polarization. That's why when you go to the beach on a sunny day, there's a lot of polarized glare coming off the ocean, or I guess here coming off the Great Lakes. And if you, on a nice sunny day, you put on sunglasses. And the sunglasses block one polarization, and then you don't have that glare. An experiment you can do, these are not sunglasses, but go to the beach one day, take your sunglasses and rotate them. You find as you rotate them, they don't work well, right? They're designed to work fitting on your nose. The orientation assumes that you want to block this polarization and let that polarization through. So what we do with our experiments is we design them to be sensitive to certain polarizations and look at the pattern of polarization we see on the sky. And the pattern of polarization can be divided into what we call E-modes. These are patterns that are symmetric if you reflect them in the mirror. So if I take these pictures and put them up to a mirror, the E-mode patterns stay the same, and the B-mode patterns flip in sign. And we can decompose any pattern into E-like or B-like. Variations in density, like the temperature fluctuations we see, produce only E-like polarizations. If we only had density fluctuations in a smooth universe, we would start out with just E-like fluctuations. We have two mechanisms for producing B-modes. One is as the photons propagate to us. As we started out early on, we learned that as a general relativist, we know that matter curves space. So that curvature of space will deflect the photon's path. That will convert on small scale some of the E modes into B modes. The other possibility is gravitational waves. So first, as light travels to us, it gets deflected. That converts some of the E modes into B modes, and then there should be gravitational waves. So here is the signal from gravitational lensing that we expect. That's shown here. Gravitational waves would produce a signal that looks like this. That's important on these low multiples. These are large angles here, small angles here. This plot's now a more up-to-date plot showing data from measuring not just temperature, which is the top curve we saw above, but even more sensitive measurements showing measurements of temperature and polarization. And for those of you who've been following cosmology, there was a lot of excitement a couple years ago when there was an announcement, not that Putin invaded Crimea, but that a claim that space ripples reveal Big Bang's smoking gun. And this was one of these interesting claims that generated a lot of excitement for good reason, because it was a glimpse into the universe's first few moments. We saw that was going to be generated in like 10 to the minus 35 seconds after the Big Bang, probing physics really fundamental scales. If correct, it would be direct evidence for the existence of gravitons, and potentially the most interesting physics result of the century. And this is what the actual data look like. This is the pattern that the BICEP group observed. And here was their famous plot that showed the red curve was what you got from lensing. The points were their data, and they saw this excess that they explained as gravitational waves. Huge bandwagon, several hundred papers cited this. Within a year, 1,000 papers. The guy who led this was named one of the 100 most important people in the world. The people involved claimed the Nobel Prize already. Very exciting. I found myself, having worked in this field for a while, immediately very cynical, because they had not, despite the fact that most of us thinking about this for a while were very worried about galactic emission. You saw how bright the galaxy was. they really had not properly analyzed that. And I felt a little bit like that little kid in the Emperor Had New Clothes. This was a great party, and some of us were ruining it. But when we looked more carefully with some of the postdocs and students at Princeton, we were able to show that we could explain this data by dust alone. And when we looked carefully at their paper, we discovered what they had done was download from the web data presented by the Planck team, scan things presented at a conference. It's a little aggressive to scan people's papers off the web. But they made the big mistake of not actually reading the slides. And what the slides said was this data included both emission from our galaxy and emission from the background galaxies, other galaxies. They hadn't corrected for that part. When you did that correction, you realized that the whole signal would go away. And this is something where, so here this is the data they downloaded. They were very aggressive in doing this. They didn't read the words on top. And in fact, they would show slides where they're missing the word not. So when you actually looked at the data they downloaded and kind of, well, I wouldn't say stole, were very aggressive about, they misinterpreted the data they downloaded, and after they've reanalyzed it, it's clear that the signals got away. This shows what you expect predicted by dust, and it turns out that the earlier claim was all dust polarization. So it seems that the claims, which had gotten a lot of press, so I wanted to make sure we discuss them, that gravitational waves have been seen. At this point, everyone, including the team that made the original claim, has now recognized it's entirely due to dust. What lessons do we learn? We better be more careful. We better understand the galaxy well. We should not hold huge press conferences before checking the results. And if your senior thesis advisor sends you a 6-page note explaining why he thinks you've done this incorrectly, you should answer the email. So where do we go from here? Well, the next step is we'd really like to do this measurement. We'd really like to see gravitational waves. We'd really like to see what they tell us about the universe. I've mentioned already that we have this telescope in Chile, the ACT telescope. What we're doing right now, and this is a picture of the back of Suzanne Staggs, who's leading the experiment with some of the students in her group building the hardware, is we're now building this at 5 frequencies. So we have the coverage to separate out galactic dust and galactic synchrotron and see not only the primordial signal, but see fluctuations on smaller scales and see what they tell us, both about emergence of structure and neutrino mass and so on. And we're right now in the process of mapping a lot of the sky. Recently, we were able to take the next big, and this is what we hope to achieve in terms of measurements. Recently, we were able to take the next big step through the generosity of the Simons Foundation, and I am benefiting a great deal from Jim Simons' generosity. He's the guy who's also setting up this Flatiron Institute. We're combining our 2 experiments in Chile. The ACT experiment, which is an experiment that's involved groups at Princeton and Penn and here at Michigan and Cornell and actually in Canada, and we've really a big collaboration at this point. With the polar bear experiment that's been mostly that out of University of California, Berkeley and San Diego. We're combining our 2 teams and our 2 experiments to build a set of telescopes and, that will be the next generation experiments here. And Jeff McMahon here is playing a leading role in helping to make this happen. Katie Fries is part of the science program. And we're looking to build something that should have the sensitivity to detect gravitational waves at more than, even if they're there, and 1/10 the level of the current constraints. So we're pushing down a factor 10. Our hope is that we'll build a follow-on experiment to this, which will make use of the same telescopes that we're calling the S4 experiment. And that would push things down by another factor 10 and make a very precise map of the pattern of polarization across the sky that will hopefully see gravitational waves, but is guaranteed to give us a terrific map for measuring the large-scale distribution of matter and seeing what the matter fluctuations look like, and using that as a probe to study how structure grows and evolves. That's going to be complemented by another big now optical survey that's happening. I think of this as the successor to the Sloan Digital Sky Survey that mapped the position of millions of galaxies. The LSST will look at billions of galaxies. This telescope will be the largest survey we've done to date of the visible universe. And it itself will be complemented by a big infrared survey. Katie mentioned the WFIRST mission. This is something I've been involved with for the past 5 or 6 years. Fun story here. I got this phone call 6 years ago from John Grunsfeld, the head of NASA's science program, who said, we just got from the National Reconnaissance Organization 2 telescopes the size of Hubble. Do you think we can use them for the dark energy work? And a lot of us, and Greg's been part of this, have been pushing to build telescopes for a number of years. And we were hoping to maybe make one with about half the collecting area. And our friends at the National Reconnaissance Organization had these 2 unused telescopes that were twice as big. They were the size of Hubble with 200 times the collecting area. And I felt it was like I'd gone to some, bad neighborhood and someone said to me, got this really nice stereo. Don't ask where it came from. Don't ask for the manuals. Don't ask too many questions, but it runs really well. And that's turned out to be true. And I actually could have, I'm now finally allowed to show you a picture of most of the telescope. But this is just a design, but not all of it, because it has dual use. But we've looked at this telescope. It looks extremely promising. We're going to complement LSST's optical map of the sky with an infrared map. We'll carry out a program of using supernova to study the properties of galaxies. We'll also use it, because it's a nice big telescope, for other areas, for looking at extrasolar planets, to studying their statistical properties, and imaging nearby planets. So I think it'll be a very powerful tool for our program. So before I turn to that, just to give people these last 3 experiments, the CMB experiment, we're doing the Simons Observatory at S4, LSST at WFIRST, are part of the program we're conducting right now for trying to figure out what the rest of the universe is made of. One of the key goals of this is to try to understand the properties of dark matter and dark energy by looking at its large-scale distribution and try to understand the strange universe we live in. Since I talked about gravitational waves, I talked about gravitational waves that aren't there, the ones that we're still looking for but were claimed. I should talk a little bit about gravitational waves that have been seen, because I think this is really one of the truly great physics discoveries of our new millennium. And this is work done by the Ligo Experiment. The Ligo Experiment operates a pair of detectors, one in Louisiana, one in Washington, that are looking for gravitational waves not generated in the early universe, but generated by the collisions of 2 black holes. And it's an incredibly sensitive experiment that is measuring motion in these long, 4-kilometer long tubes of the motion of these test masses, where it's measuring shifts in position on the scale of a shift of 1 nucleus. And this is the stunning data that the LIGO team reported. And these are, again, one of these wonderful sets of data. Again, very different from the microwave background data, but I think has, to me, a similar feel, in that we have these 2 experiments. Here's one in Louisiana, one in Washington. They see the same pattern shown in red and blue. The 2 experiments agree well. And the underlying curve is the theory predicted by what you get when two black holes collide. Our theory of how general relativity behaves does a beautiful job of reproducing the pattern we see when two black holes merge. This is exciting test of general relativity. It's the most precise test we have. It's, in many ways, it is a tremendous new window into studying properties of black holes and looking into the physics of the universe. As a cosmologist, it sort of reinforces my kind of comfort using general relativity. Because one of the things that worries me about the story I've told you is we start with general relativity, and then we end up with dark matter and dark energy. And those are two strange things. And you worry, maybe we've made the wrong assumptions. Maybe general relativity needs to be replaced. It's a 100-year-old theory. Maybe it's time for it to go. Maybe we need the next theory. But the fact that it's been so successful on these scales with black holes suggests that it's doing pretty well. And it suggests that when we're hearing the universe, it's playing Einstein's tune. So let me conclude. I want to convey to you the tremendous progress we've made in cosmology in the last couple decades. And the fact that we now have this model of the universe that's both very simple, handful of numbers, fits this data with tremendous precision. And for me, it's been amazing to watch as first we get, as our data keeps improving by factors of 10, as we go from one experiment to the next, our error bars get smaller, the model still fits remarkably well. And that's the we understand the universe side. I also want to stress that we don't understand the universe side. We don't know what dark matter is. We don't know what dark energy is. We don't understand the origin of the universe. We don't really understand the physics of the accelerating phase. So we have a lot of challenges as both as theorists to try to understand these things. And on the experimental side, we have the opportunity to, and we're in the midst of building the next generation of experiments, things like the Simons Observatory and LSST and WFIRST, that I hope will give us new measurements that will give us insights that will answer these questions and let us know what's going on in this strange universe. So let me stop there. Thank you.